Think about it. We are absolutely surrounded by computers. They handle our money, our travel, our health, even our elections. We just trust them. We expect them to work perfectly all the time. But what happens when they don't? Today, we're diving into that critical world of computer reliability and what happens when these systems we depend on, well, fail. I love this quote from Douglas Adams. It just perfectly nails the strange paradox of our super complex world, right? We build these systems that are supposed to be foolproof, but that very complexity can make any failure totally catastrophic and almost impossible to fix. It really sets the stage for everything we're about to get into. And yeah, that's the big question for us today. What are the real ripple effects when a system that we absolutely depend on, one we just assume is infallible, suddenly breaks? Well, the consequences can range from just, annoying and inconvenient to something truly, truly devastating.
Okay, so to really get a handle on this, we've got to break it down. Not all failures are created equal. They can come from simple human mistakes, from flawed logic buried deep in the code, or even from weird, complex interactions between different parts of a system. Let's start with the most basic kind of error.
This is the classic garbage in, garbage out scenario. The computer system itself might be working just fine, following every single instruction perfectly, but if the information you feed it in the first place is wrong, well, the results are guaranteed to be wrong too. It's a simple human mistake, right at the source, but it can have these massive, system-wide consequences. And these are not just minor typos we're talking about. A data entry error in Florida might have actually changed the outcome of a presidential election. Faulty data in a national crime database? That's led to innocent people getting arrested. I mean, look at Terry Dean Rogan. His life was turned completely upside down, arrested 5 times, all because of a persistent data error. These examples show you crystal clear how one simple mistake can have absolutely life-altering consequences. Okay, so let's level up to the next kind of failure, the software bug. In this case, the data going in might be perfect, but there's a flaw in the program's actual logic. The code itself is the problem. It's what causes the system to do things the programmers never, ever intended. And this is what that can look like. Christmas Day 2004. Comer's entire fleet of planes grounded. It wasn't because of bad weather or mechanical problems. It was because their crew scheduling software hit a bug it just couldn't handle. A single software glitch caused a total system meltdown, creating travel chaos for 30,000 people on one of the busiest travel days of the year. Being stranded at an airport is one thing. It's awful, for sure. But as we rely more and more on software for, well, everything, the stakes get so much higher. Now we're going to look at cases where a software failure went way beyond inconvenience and straight into catastrophe. And here's the crucial thing to understand. The exact same kind of logical error that might cause, say, a billing mistake in one system can have life or death consequences in another. A bug isn't just a bug. Its impact depends entirely on the system it lives in. The context of the code is everything. Let's look at our first case study here. This is the Ariane 5 rocket. It literally self-destructed less than a minute after it launched. The investigation later found that the cause was a tiny piece of reused code from an older, slower rocket, the Ariane 4. A number representing the rocket's horizontal speed got way bigger than the original software was ever designed to handle, and that caused a data conversion error that just crashed the whole guidance system. And the price tag for that one little bug? $500 million. All of those satellites and the rocket itself just gone. Vaporized. Talk about an expensive lesson in why you have to be so careful when you reuse code without retesting every single one of its assumptions. Okay, now we need to talk about one of the most sobering and famous cases in the history of software safety, the thanx 25. This was a medical device. It used a computer to deliver radiation therapy to cancer patients. This was a machine that was literally designed to save lives. But over a period of about 20 months, this machine delivered massive radiation overdoses to 6 different patients. 3 of them died as a direct result. This timeline is just chilling because it shows this pattern of repeated failure. The same kind of errors happened again and again before anyone really understood the root cause. So what was it? Well, one of the main culprits was this really tricky type of bug called a race condition.
It's what happens when the timing of events completely changes the outcome. So imagine you have two tasks that are racing to get to the same piece of information. Depending on which one gets there first, the result can be totally different. With the Thanx 25, an experienced operator who could type and correct data really fast, within like 8 seconds, could trigger this race, putting the machine into a state the programmers had never even considered, and causing it to deliver this massive raw beam of radiation.
But honestly, the ultimate problem wasn't just this one bug. The really critical point is that the designers had made a fatal decision. They took out the physical hardware safety locks that were in the older machines, and they put all their trust in the software to handle everything. There was no backup, no physical failsafe. So when the software failed, and it did fail, there was absolutely nothing to stop the catastrophe. Disasters like these, they were a huge wake-up call. They forced the entire computing world to get really serious about reliability. It wasn't enough anymore to just write code that, worked most of the time. The industry needed a disciplined, structured way to build software that you could actually trust with people's lives. And, this wasn't exactly a new problem. Way back in the 1960s, as computers got more and more powerful, programmers were really struggling to build big, complex systems. Projects were just a mess, always late, way over budget, and full of bugs. This whole period was called the software crisis, and it's what led to the creation of a whole new discipline. And that discipline is software engineering. The key word there is engineering. It's about treating software creation not like some kind of art form, but like a formal engineering process, with methods, with tools, and with a heavy focus on producing software that is reliable and can be tested again and again. The process is really methodical. First, you have specification. That's where you figure out and define exactly what the software needs to do. Then comes development, the actual designing and coding. After that, and this is so important, is validation. That's the formal, rigorous testing part. And finally, you've got evolution, because software is never really finished. It has to be maintained and updated its entire life. But here's the thing. Even with a super disciplined process, perfection is just impossible. And that brings us to the final and maybe the toughest part of this whole story. How do we actually test these incredibly complex systems? And when things do go wrong, because they will, who's responsible? So when it comes to testing, there are these two key ideas, and the difference between them is huge. Verification basically asks, are we building the program right? Does our code do what we designed it to do? It's all about finding bugs. But validation asks a much deeper question. Are we building the right program? Does our design, our model, actually reflect reality? You see, you could have a perfectly verified program with 0 bugs that still fails because its basic assumptions about the world are just plain wrong. This leads us right into the legal minefield of liability. Who pays when software fails? For the longest time, the answer was buried in those shrink-wrap licenses, the agreements you accept just by opening the box or clicking install. And the courts have really wrestled with this. As you can see here, the rulings are all over the place. Sometimes the agreements get thrown out, but other times, like in that Mortensen case, a company was not held liable, even when its software bug cost a construction firm almost $2 million. And this quote from the people who wrote the definitive report on the Thanx 25 accidents, it just brings us right back to the beginning. It's a fundamental truth. No matter how good your process is, no matter how brilliant your engineers are, you can never prove that a complex piece of software is 100% free of errors. There is always another bug hiding somewhere. So, we have to end here. If we accept that perfect software is impossible, if we accept that there will always be another bug, that leaves us with this huge, critical question for our digital world. Who should bear the risk? Should it be the company that makes the software, the person who uses it? Or should we all share it somehow? There is no easy answer here, but it's a question we all really need to start thinking about.